Alright, let me talk about exercise 9.4.7. Here we have the set H4 that has 4 elements, 1 minus 1i and minus I. These are in fact the fourth roots of unity. What does that mean, fourth root of unity? Raise any one of these to the fourth power and you get 1. 1 to the fourth is 1, minus 1 to the fourth is 1. I to the fourth, you can work it out as 1, minus I to the fourth is 1. These are exactly the complex numbers whose fourth powers are equal to 1. All right? And we talked about that in the complex numbers chapter. All right. So first, use proposition 9.4.5, prove that H is a subgroup of T. T was the unit circle group that we proved in the previous exercise. Now you should first verify that H is a subset of T. Part B is what is the order of H4, and part C is prove or disprove that H4 is commutative. There should be a 4 here. Hopefully you understood that. Let's go to part A. As before, proposition 9.4.5 entails 3 properties: the identity property, closure under the group operation, and closure under inverse. But as noted in the problem, it says that first you should verify that H is a subset of T. So I did that first. First note that H is a subset of T since the modulus of 1 is equal to modulus I, modulus minus 1 is equal to 1, so they're all in the group T. All right, so that takes care of the fact that H is a subset of T. H is a subset of T, we've established that. So let's go ahead and establish the identity property. All right, now we know that 1 is the identity, and 1 is in H, or H4. Put the 4 there. I'm going to leave off the 4, just understand the 4. Okay, so that gives me the identity property for H4. Number 2, closure under multiplication. There are 2 ways to do this. One way is to simply make a Cayley table and show that the Cayley table is closed. All the entries in the Cayley table are equal to the entries on the margin. That's one way to do it. That's a straightforward way. Another way is to use properties of the definition of H. H is the fourth roots of unity, so Z is in H if and only if Z to the fourth is 1. So if we want to show that the set H is closed under multiplication, all we have to do is show that multiply any 2 elements of H together and we still get something that has fourth power equal to 1. Okay, so let's suppose that Z and W are both in the set H. Then ZW to the fourth is Z to the fourth, W to the fourth. That's usual algebra, which applies to complex numbers. We showed that associative property. Actually use commutativity also. And that's equal to 1 times 1, which is equal to 1. So that means that ZW is also a fourth root of unity, so ZW is also in H. All right, so that's the other way. If you're confused about what I just proved, go ahead and use the Cayley table instead. That's always a straightforward and foolproof way. Now to show the, whoops, I forgot the number 3. This is for number 3. There are 2 ways to prove number 3 as well. One is to use Cayley table, show that every entry in the Cayley table has an inverse. Another way is similar to the second way I proved part 2. Take any Z in H, and you want to show that its inverse is also in H. Now, if Z is in H, then Z to the fourth is 1. We can take the inverse of both sides, so Z to the fourth inverse is 1. All right, now Z to the fourth inverse is Z inverse to the fourth. We have that from proposition 9.3.24, part 2. All right, so we can write Z to the fourth inverse as Z inverse to the fourth. So Z to the inverse fourth equals 1. Therefore, Z inverse is also in H. So that proves the inverse closure property. All right, so let's go back up to parts B and C of the problem. Part B says, what is the order of H4? And H4 is the number of element, which is 4. So prove or disprove that H is commutative. Well, H is a subgroup of T, and T is commutative. Therefore, H is commutative. And that finishes the problem.